I shan't sing it to you, but the tagline to that would be, and I feel fine. So my view is not quite so apocalyptic as Michael Stipe's is, but I want to say there is something going on here, and I've got some ideas of what we should be doing. Quick introduction to myself. I've been working around with embedded Linux since 1999, and around about 2002 I started training people on how to use embedded Linux. So I'm a freelance consultant. I've been using this stuff for a lot of time. I've seen lots of different projects and lots of different people doing the same kind of things and stumbling into the same kind of problems. I have a blog, which I highly recommend you go and see, www.embedded-linux.co.uk. It's fairly intermittent. I haven't updated it in a little while, but there's some stuff there which you might find interesting. And my company website, if you're interested, is tunex.co.uk. So that's me. So essentially what I want to talk about then is how do we get to where we are now, so the last 10 years of embedded Linux. Where are we now? So I've got a couple of slides on problems that we've solved and problems that we still have, and where do we want to go in the future. And I want to look at a number of different issues or a number of different options of where we can go from this point onwards. So over the last 10 years or so, things have changed quite a lot. 10 years, well, this is a slight exaggeration. Slightly more than 10 years ago, this was state of the art. RPX Lite or something like that. Hands up here, anybody who used the RPX family or similar machines?
Showing my age.
Yeah, you're all youngsters, that's the trouble. So this is typically what we're working with back then. Fairly low power, low clock speed, not very much RAM, very little storage. And PowerPC was dominant at that point. ARM was practically nowhere in embedded. Fast forward to today, a typical embedded board, well, PandaBoard ES is one that I mentioned. Dual core, Cortex A9, 1.2 gigahertz, more RAM than you can possibly imagine, more storage than you can possibly fill up with big boxes. So things have changed quite a lot. So putting that into perspective a little bit then, given those two boards, which I've slightly juggled to make it a little bit more extreme than it would normally be, we see that clock speeds have gone up 15-fold. The amount of RAM we have has increased 64-fold. But the real outlier, the real thing that's really changed is the storage. That, on my example there, has increased 512-fold. And bear in mind that over a 10-year period, following Moore's law, if we take Moore's law to be doubling in capability every 2 years, that would be 5 doublings, so you'd expect a 32-fold increase. So clock speed and RAM size are kind of roughly along that line. Storage has increased way beyond that, mostly because of the transition from NOR flash to NAND flash, and in particular to commodity NAND flash in terms of SD cards and such like. So the world is changing, and it's also changing here in the amount we expect to pay for hardware these days. That's the one thing that's gone down. All of this, of course, is very good news. I'm not. I'm highly in favour of all of this stuff. This cost thing is partly down to this fellow here, the Beagle board. In my opinion, the Beagle board was a bit of a game changer because it's cheap, it's available, Everybody knows what a giga board looks like, even people who wouldn't normally have any vision for embedded Linux. In fact, to some people, embedded Linux is a giga board. Oh, I do embedded Linux. Oh, you mean the stuff that runs on a giga board? That's it, yes. So this made a big difference. It also provided a platform, a standard platform. So a lot of people now doing embedded Linux development will start off with a giga board. And giga board is supported by most of the main distributions, etc., etc. So giga board is a focus, is a platform for embedded software. And also similar things like Panda board and Raspberry Pi and so on. Okay, so that's the hardware side of it. Switching over to the software, the kind of things that define embedded Linux, the kind of problems that we had to solve 10 years ago, well, 14 years ago in actual fact, were these kind of things. Most embedded hardware was not PC-based, not x86. We had custom hardware, so we had to go in there and start hacking the kernel and make it work on lots of funny bits of hardware. Didn't have much RAM, not much storage, etc., etc. So we had a whole bunch of problems to solve in order to make Linux work on embedded hardware of the day. And we responded, the community responded, with things of this sort. Cross-compliance was a big issue some little while back. If you read an embedded book, a book about embedded Linux from 10 years ago, you'll find chapters and chapters devoted on how to cross-compile, how to create a cross-compiler, how to take GCC and make a cross-compiler out of it. Cross-tool and then cross-tool MG came along, and that made it a lot easier. And now cross-compilers are readily available. But that was a big change. BusyBox. BusyBox probably was the key thing. Without BusyBox, embedded Linux probably wouldn't exist in the format that it is now. So BusyBox was another very important tool that came along. Flash memory support. 12 years ago, we didn't have any flash memory support in Linux. Then along came Axis Communications, we had it in the MTD layer, they added in JFS and then JFS2, and we had flash memory support, and so on and so on and so on. So embedded Linux really is it's not a real thing, it's a list of techniques you can use to make Linux work on typical embedded hardware. Now, how many of you have been through this kind of cycle? So this is the typical day's work of an embedded engineer. Well, more than a day, a few months now. So every project you start off, your boss comes in one day, hey, we've got this really great idea, we're going to be using Linux on our next product. And you go, oh my God, what's that? Well, it means you've got to find a tool chain, you've got to get a copy of Ubuntu and hack that around until it works. You've got to get a kernel and hack that around until that works. Then you need to start thinking about the root file system, the user space, and get something there and tinker with that until that works. And then when you finally get to the point where everything works, you say, ship it. And that's it. And then once you've shipped it, you go through the whole cycle again for the next product. Okay, so it's a little bit of a labor-intensive job. So that's kind of the past. That's how we got to be where we are, in my opinion. So where are we now? Where's that point on the map? Well, from the stuff we've been talking about hardware, most of those, well, a lot of the problems have been solved. We have pretty powerful processors available to us for very low prices. We have more RAM than you can imagine. We have more storage than we can possibly use. And there's some stuff here also about the change from the technology. The raw flash memory is kind of disappearing. We're switching to more commodity flash. So I believe that we are at a kind of inflection point in embedded Linux. In actual fact, we're kind of past it. If I thought about it earlier, I would have done a nice little diagram, a kind of Mark Shuttleworth kind of diagram with two lines intersecting and sort of 2011 written on it or something, but I didn't do that. But we're kind of at a point where embedded Linux has kind of finished its first phase, and we're entering a new phase where we have all this wonderful hardware available to us, lots of capabilities. How do we most effectively use all that stuff? So we have some new problems. We've solved the old problems, but as is the rule, whenever you solve a problem, you create a new problem. We'd be out of a job if that wasn't true. So the new problems we have, there's really two vectors here. The first vector is complexity. The devices we are using today are far more capable than the ones that we had 10 years ago. And not unnaturally, people want more from their device. Moore's law applies to embedded as much as to anything else. So the thing you're creating these days has to do a lot more stuff. It's no longer adequate to have a user interface that's 2 buttons and a 7-segment LED. You could have a touchscreen, and that touchscreen has got to work like a smartphone. You've got to be able to do pinch and zoom and flick and all that kind of stuff. And it's got to do fancy animations. So what we're trying to achieve now is far more complicated than what we used to do. Bringing along with that is the issue that if you've got all that software in this box that you're about to ship, if you've got several gigabytes of software in there, you've got several gigabytes of bugs in there as well. So whatever you do from this point onwards, you are going to have some mechanism for doing automatic field upgrades. I had an interesting conversation with David Tatt yesterday. He's the buffer bloat guy. One of the issues that he highlights is that one of the things that makes buffer bloat difficult to fix is because we have slightly misconfigured TCP/IP stacks in lots of infrastructure scattered across the globe. Most of that infrastructure is running Linux, of course. But without the ability to push updates out to all that infrastructure, it means that the problem is going to continue for a little while longer yet. So I'll say it again. Any device any of you guys in this room are designing now, you are going to have to build in the ability to do updates and to do bug fixes remotely. That's a given. So the first vector then is complexity. The second vector really is really summarized in this bit here. We're doing a lot more stuff these days. We're shipping a lot more devices as an industry. But the number of engineers hasn't really increased that much. So there are too many devices and not enough engineers is a basic problem there. So making embedded devices has got to get easier. Not specifically for you guys in this room, because you guys are all geniuses, I know that. But the other guys, not everybody is as smart as us in putting together embedded Linux systems. So it needs to get easier. Not too easy, but it needs to get a bit easier. So the main part of this talk really is my kind of view of what an embedded operating system should look like. And I've come up with quite a number of desirable features. Possibly slightly too many, but I'll go through them anyhow. So my ideal embedded operating system should have all of these things. Completely open source, I think that's fairly obvious, we'll let that go. Architecture support, as many as possible is a simple answer, but the main ones are, of course, ARM, MIPS, PowerPC, x86. If my OS supports those architectures, I'm in a pretty good place. Availability of board support packages. First of all, I want to be able to fairly quickly get some standard hardware up and running. So I'd like to be able to take my Beagle board, download an image, have it up and running in a couple of minutes. That's kind of a nice to have. Crucially, of course, I must be able to create my own board support packages and integrate that with the operating system. I'll amplify each one of these slightly more detail in a few slides' time. Flexible. By that I mean I want to be able to use this operating system for a wide range of different applications. Minimal base install. Okay, so we've got all these gigabytes of storage, but in reality we don't want to use more gigabytes than we need to. So I don't want an operating system that requires 4 gigs to start up. I'd like to come in a little bit below that if I can. Flash friendly. This is one of the bees I have in my bonnet. Obviously, when we're putting together these systems, we want to preserve the flash memory as long as possible. So, no swapping, obviously. We want all the volatile directories to be truly volatile. I mean, who ever thought it was a good idea to make temp be a non-volatile directory? Temp is temporary. Obviously, it should be a tempfs, but it generally isn't by default. And my favourite and crucial one, I believe, root file system should be read-only. There is no good reason for a root file system to be read-write. Part 2. System logging is a real problem. And I'll have to try this again later on. But there's another one of my bugbears is that there's no decent system logging in Linux. And I could do a whole talk about that, but I'll skip that for a moment. In-field update we've mentioned already, that's kind of crucial. Fallback boot, here's another thing. Almost every project I've worked on, at some point or other, somebody said, what happens if we brick it? We need some mechanism for restoring the system back to life, either by pressing some funny combination of keys or doing an auto restore or whatever. But every system needs that, and every system does it differently. I've engineered half a dozen or a dozen different recovery mechanisms for different organizations. It'd be nice if we just did it once instead of having to do it differently each damn time. Debug tools, yeah, that's kind of obvious. Touchscreen support, we'll skip that. Long-term support. I got into trouble saying this with a certain person. Again, if you are going to produce a device and put it out in the field, it needs to be maintainable. You need to be able to update that device, and therefore you need to keep on doing that for the life cycle of that device. It's no longer a case that you put it in the box and ship it. That is not the end of the relationship with that device. That is basically your device until it finally gets chucked into landfill. Oops. So that's ideally what I want. So what have we got at the moment? Or rather, what could we base our ideal operating system on? So I came up with 3 scenarios that I think are viable. Why not use a mainstream distro, Debian, Ubuntu, or whatever? We can do that now. We have the storage, we have the memory, we have the processing power. You can run Ubuntu or Debian on a Panda board or a Regal board or whatever. So why don't we just do that and just have done with it? So I'm going to consider that as one option. or use an embedded distro. Open Embedded or Yocto are a lot of Yocto people around here, and similar things. Why don't we use one of those? After all, it's got embedded in the name, that's got to be the right thing to use, yes? So, why not? So let's think about that. And then, of course, there's Android. That is another embedded Linux distro. Why not use Android? There's several 100 million people out there doing it already. Why don't we just join them? So, looking at these three options, I'm going to go through each one of those topics I mentioned on my embedded ideal embedded OS, and I want to see what the issues would be with each one of them. And so, I've kind of come up with a crude scoring system. So, purely randomly, really, I've given each one a score out of 10 for each one of the, I think, 12 different features. And just a few things still further, I marked them MS for mainstream distros, ED for embedded distros, and AN for Android. Hopefully you'll get the hang of it. So, the first option, the first requirement I came up with is fully open source. So I think we can give them 10 marks each for this. All of the three options I'm looking at are totally open source.
Android aren't open source.
Android is open source, sure.
Crucial parts aren't.
There is enough. No, if you go to the Android open source project, AOSP, there is enough there to produce a working system.
Sure, but it's not realistic.
Well, okay, I haven't really got time. If I can take questions at the end, otherwise this is going to get, this is going to turn into a bit of a bear. So, just bear with me, this is my opinion. So, I repeat, all of these are fully open source. I'm not considering anything that requires any proprietary components. Architecture support. Okay, this is where things start to fall apart slightly. Most of the mainstream distros now do have some support for non-PC architectures. Ubuntu only support ARM version 7, but others, Debian for example, support a whole range of things, including PowerPC and MBits, and some other stuff as well probably. So there's a mixture there. But there's quite good support if you look around for the architecture that you want. Embedded distros, naturally, that's what they're about. They support a wide range of architectures. So they score a 10 for that. Android is kind of getting better. It started off with just ARM. Its more recent releases of the AOSP include also x86 and MIPS. As one of the key architectures. And there are, is anybody from Mentor Graphics here? I know, of course, you do ports for PowerPC and other stuff too. So that's not a bad story. Board support packages, right. This is where I have a real problem with mainstream distros. They're not really geared up for having custom kernels and custom bits of hardware. So it can be done, but it requires a certain amount of fiddling about. And I'll come back to this again later on, but the key thing is that a BSP, a board support package, isn't just a custom kernel, it's also a bunch of modules, it's a bunch of configuration options, and it's probably some custom utilities, and of course it's the GPU, library, and some other stuff. So it kind of invades quite a lot of the system. And pulling all those pieces apart and putting them together again is a little bit tricky. Linaro have quite a nice tool for doing this. Linaro Media Create, I don't know if you've ever used that, but essentially it allows you to take all of those board-dependent components and join them with a binary, which is the rest of the OS. But of course, Linaro is not a distro. Anybody from Linaro here want to contest that?
It's supposed to be a distro.
Absolutely. But if you go to your website, it kind of says that you are.
We've been a tad confused about this so far. We're trying to be less history.
Excellent, I'm glad about that.
They're engineering builds is what it's called now.
Yeah. I'm perfectly happy with that, that's good. Where was I? So, board support on a mainstream, and I'm thinking Debian in particular here, it can be done, but it's a little bit tricky. Not usually, but it requires a bit of thought. Embedded distros, yes, typically, I'm thinking about Yocto here, you set up your recipes and your layers, and that's your board support, and then you go bit bake, whatever it is you want, and it puts the whole thing together for you. So that's nice and neat. Likewise with Android, you do the lunch combo thing, and that essentially is the same thing as what Yocto does. So the scores, and the scores are, mainstream distro is not that good, embedded and Android, yeah, they work. Flexibility, in other words, what can you do with this thing? This is where the mainstream distros come into their own, of course. They are very flexible. They have tens of thousands, well, thousands or maybe tens of thousands of packages. You can put together a lot of different systems using those packages. So, top marks for that. Embedded distros are a little bit behind the curve on that. They generally have 1,000 or so packages you can choose from, so slightly restricted is what you can do, but it's good enough. Android, on the other hand, is basically only good for one thing. It's a monolithic operating system. If it does what you want it to do, that's great. But trying to repurpose it to do something entirely different is not that easy. So I'm giving that 0 for that. Android has, as it says there, many thousands of apps. But those apps aren't particularly what I'm thinking about, and aren't particularly useful for the kind of things that we are likely to be using. Minimal base install. Okay, so like I say, I may have 4 gigabytes of memory, but I don't want to use it just for the operating system. Most operating systems, most mainstream distros do have a kind of minimal configuration. With Debian, you have MDebian grip, which comes in at about 100 and something megabytes for a basic console app. Ubuntu core comes in at about 200 to 250 megabytes. Can't remember exactly. So, kind of big, but not unacceptably big. Embedded distros, well, okay, this is where they're good at. If you do a bit bake console image, you'll end up with something of the order of 16 megabytes to 32 megabytes, something like that. Quite a small amount. So that's good. Android, again, because of the way it's put together, you either have all of it or none of it. So a default build of AOSP for Jelly Bean comes in at around about 160 megabytes, which is not so big. It's acceptable. But you can't kind of make it any smaller than that. You either have the whole damn thing or none of it, unless you want to spend a lot of time making that with it. So in terms of the size then, embedded distros obviously are the best here. The mainstream and Android, they're a bit bigger, but they're not out of the window, so they're okay. Flash-friendly configurations. So here the main things I'm looking at are anything we can do to preserve or prolong the life of our flash memory. So no swapping, volatile tongue, and read-only root file system. Mainstream distros. So by default, all of those things will be the wrong way. But it's relatively easy to go in and turn off swap. It's just a change to FS tab or something. And while you're editing FS tab, you can make temp be volatile. Not a big deal. Read-only root. Most distros are not designed for read-only root file system. With Debian, with a bit of fiddling around, you can make Debian work okay with a read-only root. So I've put hard there, it's perhaps a little bit of an exaggeration, but it requires a bit of thought. With Ubuntu, I've never managed to get Ubuntu to boot with a read-only file system, read-only root. I don't know if anybody here has ever managed that.
Fedora has read-only root in the Fedora 18. Fedora 17 and on up uses read-only root.
It does?
Yes.
Wow. Top marks. I'm not a Fedora user by default, so I'm not so... I don't mention it that much, so I apologise for that.
It's supposed to work in Debian, so bits of it doesn't, but it's probably not very well used. So.
Yeah. There are, I mean, I don't want to go into details, but there are particular issues with resolve.conf. There are some issues with UDEV, I think. So you need to do a little bit of tweaking to actually make it work properly. But it can be done, but it's kind of not default. You need a little bit of skill to know what to do there. Okay, embedded distros. This is the thing that I really think embedded distros should do out of the box, but they tend not to. In my opinion, anything that calls itself embedded should have a read-only root file system. So, talking to the Yocto guys just now, turns out that you can configure Yocto to produce a read-only root file system, but it doesn't do it automatically, and you've got to, you know, there's a little bit of effort required there. The big winner here, in my opinion, is Android. Android is an excellent model for how an embedded operating system should be. Android has read-only root by default. All your Android devices have read-only root file systems. So I'm giving Android top marks for this. And the others, maybe I'm being a little harsh here, but they're trailing behind a bit. System logging. Oh, don't get me going on this. This is the main message. Minimal requirement here is that the system logger doesn't wear out my flash memory in a month and a half, as can happen if you're not careful. The problem with system loggers is by default, they will write log files to varlog messages or something. And the way they do that, you end up with a lot of small writes, and that's the worst thing possible for flash memory. Because that requires, well, that will end up with a lot of invalidations, a lot of erase cycles, and your flash memory will get erased quite quickly, will wear out quite quickly. And if you try doing this with JFFS2, you'll find the garbage collector kicks in and takes up 100% of your CPU, which we don't want.
Actually, the Android logger doesn't write to Flash.
Yeah, there's no persistent logging in Android.
Oh, always good.
That's been here.
Yeah.
So, minimum requirement then is that the system log utility should not write to flash memory. The minimal implementation of that then, if you use BusyBox, syslog D with a minus C, then it will log to an in-memory ring buffer. So, no flash writes.
And no logs after reboot.
That's right.
Well, what can you do?
You get one or the other.
Well, I'll come back to that in a moment. So, embedded distros, yeah, they'll do. BusyBox syslog will be used by default. That's as good as it gets right now. With mainstream distros, I haven't had a quick look. Most of them do allow you to install a package, BusyBox syslog D, and you can configure that package with a minus capital C. So with a little bit of tinkering with a mainstream distro, you can make it as good as an embedded distro. It's still pretty rubbish, of course. And with Android, Android has this thing called logcat, well, kind of, which is basically the same as BusyBox syslogd with the -c. In other words, all the logs are written to memory, so they don't go out of flash memory. Now, as somebody said, this is not ideal because it means that the log is volatile. You have no permanent record of that. Which is why I say this is a whole area that somebody in this room, in this conference, needs to look at. Because Linux is fundamentally broken in this area. The logging in Linux doesn't really work. And not only this, but also the thing that really drives me crazy is that half the daemons you use also have their own logging facility. So if you use Samba, that has its own bunch of logs. Apache has another logging mechanism. Cups has some other crazy stuff. It's a disaster. However, so nobody gets very high marks for this. The embedded distributions in Android gets kind of the best of the bunch because they at least don't wear out your flash memory ahead of time. The remote update thing. So the basic idea here then is that if we've got a complex system with bugs, we know there'll be bugs in there, software always has bugs, then we need a mechanism for updating this in the field. Again, nobody really handles this very well. In the worst case, with a mainstream distro, if you're not careful, when you do an update, if you do an apt-get apt-get upgrade, it will brick your system. That's happened to me a few times. And the reason it bricks your system is that it merely downloads all the packages, which include things like new versions of the modules, but it doesn't update the kernel, and then the system won't boot. So, again, it's not a huge problem, we can solve it, but it's again something that you've got to think about and come up with your own way of getting around. So, yeah, don't handle it all. Embedded distros are a little bit better. Again, the thing is slightly different here because with embedded distros on Android, you're basically in control. If you ship a system with Yocto or with Android using their build systems, then whenever you want to do an update, you're going to have to go through and do the build again and then ship those components out to the field. So it's kind of a different kind of thing because you're in control, you therefore create the BSP, and the BSP, hopefully you test it beforehand, will do the right thing. But it's still an absolute pain in the neck. There ought to be an easier, industry standard way of doing this stuff without bricking your device. Oh, the other thing, yes, fallback boot. This is the idea that if you do brick the device, there should be some way of recovering it. And again, every device that I've seen has such a thing, but again, it's all proprietary, it's all different every time. There ought to be one good way of doing it rather than several thousand kind of okay ways of doing it. Coming to the end now then, user interaction. I don't go too much on this. The main point here is that if you have a touch screen, people want that touch screen to behave like a smartphone or something similar. So, not naturally, Android is the best thing to do that. If you want a touch screen interface, use a phone operating system. Stepping back a little bit, mainstream distros, they're all kind of groping in that kind of area. And these various things like GNOME Shell and Unity and so on, they're all kind of trying to do the phone thing on the desktop with varying degrees of success. I don't want to go into the detail, into the pain of that. But they're kind of getting there a little bit. Mainstream distros don't really go in for this stuff. in my opinion. So yes, you can install factory install, blah blah blah, but it's not an easy thing to do. So points for that. Android scores because that's what he does. The others, somewhere behind.
So embedded just for the Opto project does support Flutter and has Sato, so there is a graphical interface for it.
But does it have the on-screen keyboard? Does it have the big icons?
Yeah,
Does it have
It
the...
had it even 8 years ago.
yeah. So
Okay.
it had it all along.
Okay. I'll ask for a demo for that later on. Sure. Skipping this fairly quickly, debug and trace tools, we need them. They more or less have that there. You can argue about the details, but it basically works. Long-term support, I would regret putting this on the slide at all. I guess the only point here is that, as I said already, if you're shipping a device, you have a responsibility to keep that device working for some period of time. And as engineers, you're going to be designing mechanisms to do that. So there you go. So this totally unscientific trawl through from this stuff. Add up all the numbers, it comes out to that. So the winner is by Whisker Android. Happy with that? Well, not really. Okay, so my position on Android is it's a fantastic embedded operating system. It does a lot of things right. But it has a number of downsides. It's monolithic, it's inflexible, and it's not a community project. So Android is good for a certain well-defined class of devices, but it's not a general purpose operating system. So no, Android is not really the winner. The main thing I'm trying to say here really is that what we should be doing is taking the good bits out of Android and putting it into Yocto, putting it into Debian and others. We should learn from what the Android guys have done because they really did a good job, and we should apply those lessons elsewhere. Which kind of says that. So essentially, I guess my conclusion as I'm coming to now is that we've come a long way. There's a lot of good stuff out there, but there isn't anything that really joins everything together into an ideal, perfect developer experience for creating an embedded operating system. And I'll say again, if anybody out in the room really feels that they want to take something on, take on logging. We need somebody to come up with a decent logging system.
How about the journal in System D?
Absolutely not.
I don't know anything about it other than lots of that System D talk.
So I would have given Android a 10 on logging. So that, especially with the new. Anyway, talk to me afterwards about logging. I have a lot of opinions about it.
Okay. So, one more slide to go, and then we can have a couple of minutes for questions, and then we'll have lunch. So, conclusion then. Yeah, I've kind of said this already, actually. So, we're doing well, guys. Yeah? No panic. But there are challenges ahead. We haven't solved all the problems. We have new problems to solve. Bear in mind then that we're entering a more complex world with more complex devices. Your role as embedded engineers has changed. Okay? The system you're putting together is far more complex today than the one you did 10 years ago. So you need different techniques for handling that. And hopefully, we, the community, will step up and solve at least some of these problems over the next year, 5 years, 10 years, whatever it may be. And that is the end of that. So any questions we have? Well, actually, we're technically run out of time, but we could take a couple of questions just to see if anybody has any thoughts on this. Literally a couple. So, you sir?
Right, first question is, you seem to have missed out something about licensing, because none of these projects seem to have a way of saying, for all the components I've just built, what licenses are they covered under, and what are my obligations if I give this to somebody else? Do I have?
Yeah, I could have covered that, but it would have taken the entire presentation, I think. So,
The Octo project is pretty good, actually. They have licensing information on all the packages.
Yeah, Ubuntu does as well.
and you can argue that Android is pretty good as well, because it's all either Apache,
Monolithic licenses.
it's basically Apache with some GPL bits. So the problem comes actually with embedded distros, which have a wide variety of licenses, and I have no idea how to cope with that.
Yeah, the Octo project will generate a manifest for you, and not only will it generate the manifest, but it will generate the source archives in such a way that you're able to just deliver that to the web, to your web for distribution to meet the GPL requirements.
And you can even filter some license out of the distro somehow.
Yeah. It's a whole topic. I don't want to go into too much depth into that. Time for one more question, you sir?
So there's a whole Python workshop going on a few meters from here, and I was wondering if you saw Python in any way as an alternative here for a certain scenario.
Somebody suggested I should cover Tizen as one of my options. I didn't, simply because I know nothing whatsoever about it, so I'm not going to make any comments. So it may or may not be an option, I just don't know.
Last time when I looked at Tizen, it was not immediately distro, and it was not mainstream distro. It was something.
I remember Migo, so I would leave that well.
For me, it's yet another incarnation of MyMO, which was done in a very ugly way, and I hope that Tizen will be better, but I decided to wait 2 years and then take a look.
I think it's very wise, yeah. Very wise.
Even 9 months, on a different name, on a different platform.
Okay, so I'm going to call an end to it now. If anybody wants to discuss any of this stuff, I'm happy to do that now or at the lunch or any other time. But in the meantime, thank you all very much for being here. Thank you.